Hello, everyone. Just trying to piece together a few things. We're getting some film together, and we're sort of piecing it together to make a hopefully decent presentation of some basics of electricity and magnetism. Essentially, it's going to be two videos. One's going to be some notes on electricity and magnetism, part one. And the other one's going to be some notes on electricity and magnetism, once again, but part two. So some notes on electricity and magnetism, parts 1 and 2. For part 1, we're going to talk about drift speed, RC circuits, and in general, RC and RL circuits, magnetism, Biot-Savart law, Ampere's law, magnetic flux, phi sub B. So that's associated with the part 1 video. I'm trying to make the two videos somewhat more manageable to look at by breaking them up a little bit. So this is what you're going to see regarding part 1 type material. So you can go here. That'll be associated with the part 1 video regarding the whole matter. So got this, and when we get to part 2 will be associated with the remainder of what's up here. So what we have here, and this will be part 2. Can use Roman numerals or not, and this will be part 2. So let me leave this up here. I'll be making the introduction based on the stuff that's up here. Not everything is in the greatest of detail. If we want more detail, and we do have more detail, it's scattered throughout the course in terms of problems that are already solved by myself and or by people that wrote books that we're using. If you're in the calc-based treatment of the class, as I'm currently talking about it, Dr. Deborah Katz and her great book pertaining to the calculus version of mechanics and pertaining to the calculus version of electricity and magnetism. So much is there. Some great resources are available to us to be able to solve problems. Hopefully I've looked at some of this stuff in a good enough manner that when you look at the solutions that I've given from that particular book, whether you're taking the class or not, I say enough in the videos that you have access to what it is that I'm trying to solve just by virtue of what I'm talking about when I'm trying to explain various things. Whether I'm talking about calculus-based treatment of mechanics or whether I'm talking about calculus-based treatment of electricity and magnetism. I speak through it quite a bit so you can actually look at some of the problems verbally that I kind of present and go through. In addition to that, the solutions are available to a lot of people. So if you get the book, Dr. Deborah Katz's book, you can look at the problems that are actually listed in the book, and you can look at my solutions that way as well, and also have films pertaining to that. The same exact thing holds when we are talking about, forgive me guys, we're talking about another great book, and it's non-calc treatment. So Dr. Deborah Katz's book for mechanics and electricity and magnetism is calculus-based, and the other great book, 2 volumes as well, just like Deborah Katz's book, 1 volume for mechanics and the other volume for electricity and magnetism. Same with Serway and Vuille, their books, volumes 1 and 2. Volume 1 pertains to mechanics, and volume 2 pertains to electricity and magnetism, and that is. And that is all, and that's non-calc treatment. So Serway and Vuille is non-calc treatment. Deborah Katz's book, her books for mechanics and electricity and magnetism are calculus-based, and Serway and Vuille, their books pertain to so calculus-based treatment for Deborah Katz's book, mechanics and electricity and magnetism, and non-calculus-based treatment for mechanics and electricity and magnetism for the Serway and Vuille book. So here they are. Many, like I said, if you have one course but not taking the other course, if you have one book or one set of books but not the other set of books, if you can acquire both sets of books, I have very many, not all the solutions possible, but I have very many solutions presented to you in PDF format on Canvas if you're in my classes. Many PDF solutions are presented on Canvas, and a substantial amount of film is presented, much of it on YouTube. So you should be able to get something out of it that way. So you really can't summarize these very broad topics in any one particular video. So you can summarize it somewhat, but you can't completely comprehensively really give a be-all presentation of topics that are just this massive. But you can point to where to look. And I've already told you, you can see it in my PDFs. You can see a lot of things in my PDFs, and you can see a lot of things in my film as well, both non-calculus based for mechanics and electricity and magnetism, and for calculus based for mechanics and electricity and magnetism. So that's kind of where we're going. Now this is what I've done for part one. As we said, drift speed, RC circuits, RC and RL circuits, magnetism, Biot-Savart law, Ampere's law, magnetic flux, phi sub B. When we get into the part two, that'll be another video, because I'm trying to shorten these up a little bit at least. We're going to talk about inductance, the inductance capacitor, the inductance capacitor circuit, easy for me to say, the LC circuit, and how the oscillation takes place. Again, we said very likely there's oscillation taking place if you have some sort of damping going on, but things tend to die out. Here, the oscillations will not die out when you're talking about something like this. So there's no resistor in here for there to be a power loss. So it just goes on. It's analogous to a spring, a mass that is on a frictionless surface attached to an ideal spring, and you extend it, you stretch it or compress it by an amount A, amplitude, and it will oscillate back and forth between the limits of where the amplitude can go. Positive A and negative A, it'll oscillate back and forth. The total energy of the system will remain the same. Same exact thing is happening here with the inductor slash capacitor LC circuit. AC circuits, we're going to go into that as well. Again, there's some limitations to how far we can go on that, but we'll try to give a decent presentation for our needs, regardless of what class you're in, whether it's a calc-based class or non-calc-based class. It should be pretty decent for us. We'll talk about the transformer, the refraction of light, and I forgot how to spell light. The refraction of light, and the mirror equation and the thin lens equation. So it gives you a little bit of look at least a good portion of what's going on here. So what I'm going to do is, if for anybody, I guess maybe perhaps the easiest way to do this is I think maybe we're going to leave this as is for an introduction to both films. The part one film, which is that material, and the part two film over here. Once we start, when we're talking about the part one film, this is substantially what we're going to be doing. If we fall a little bit short, we'll do it into the other video. That's not an issue. But roughly speaking, this is what the part one video is going to entail regarding, and the video itself, both videos are going to have the title, some notes on electricity and magnetism. The part one is going to look like this. So if you're looking at this now, this part of the film, and it's attached to the part one video, this is what we're going to try to do. Later on, in the part two film, and I'll make this kind of like a universal introduction to both films. Here will be the part two film, and you'll see this is what I'm going to try to attempt as well. So depending which film you're seeing this on, it'll tell you what we're going to be doing. If you're looking at part one film right now, this is what we're going to do. If you're looking at part two film right now, this is what we're going to do. So that's about it. Everyone do great, and I hope this helps. Take care. Forgive me, one last thing to say regarding that. Again, so here we go. You're gonna be seeing it. So right after I'm talking right here, this will be the introduction to both some notes on Electricity and Magnetism Part 1, and it'll also be the introduction for the other film, some notes on Electricity and Magnetism Part 2. Good luck to you guys. Hello, everyone. Thank you for joining. There are a few things I'd like to bring forward in our study of electricity and magnetism that hopefully can be of some benefit. There's obviously a tremendous amount of content out there that's beneficial to us, and at the same time, at what level we're going to be asked to handle certain matters obviously plays a role. So I'm going to try to make this consistent with some of the questions that you could be asked, and you know, this much of what I write here could apply and should be able to apply to a calculus-based course and to a non-calculus-based course. If there are some things that we do in a calculus background, obviously, if people are not familiar with the calculus that's used to arrive at the conclusions to which we arrive, that's not a real big problem. Just know what the conclusion is at least, and then you'll be fine. If it's a calculus-based course, it's good to know how something arises through the use of the mathematics called calculus. If you don't have that background and it's not asked of you in a non-calculus-based course, that's not really a big deal. Just know what the conclusions are and be able to work with them. So that's so as such, many of these videos can work for an electricity and magnetism class, regardless of whether or not the class is based has a calculus base to it or a non-calculus base to it. So there are two, you could say two packets pertaining to what I'm going to discuss today, and they are the one in, you know, as you're watching this, the one to your left is, you know, some notes on electricity and magnetism, and the one to your right, RC circuits and RL circuits. I'll try to keep the RC circuits and RL circuits kind of pretty much into this packet right here, or put it into this packet, so it should make some sense when we need to do that. Well, here's some general notes, by no means exhaustive of everything that's out there. I mean, when it comes to everything that's out there, I mean, I don't think anybody knows everything that's out there, but we can know a whole lot, and we can know a decent amount pertaining to much of the discussion that we're trying to bring forward here. So regarding some notes on electricity and magnetism, let me say a few things and see how you might feel about it. We talk about, I'll roughly follow this packet. Like I said, oftentimes I have these packets will scroll at the end of the video. So that, you know, if possible, we'll do that as well. For those of you who are physically present in the classes that I'm teaching, you'll see this, I'll definitely have these on Canvas. But perhaps, at least the goal is to try to also have this to scroll at the end of the video. So that'll be a benefit as well to anybody not associated with the course and doesn't have access to the Canvas aspect of the course. Well, we're looking at this, guys, and we can say a number of things. Let's talk about drift speed, as we were talking about. Now, I'm kind of giving a bit of a review because we're toward the end of the semester, and being that we're toward the end of the semester, you've seen all this stuff, and it's just good to get a refresher sometimes. So when we talk about drift speed, they're saying delta Q, the change in the amount of Q that actually flows somewhere, is going to be equal to the number of free charges per, the number of free charge carriers per unit volume, times the volume will tell you the number of free charge carriers. And if you multiply that by the charge on each of those free charge carriers, which is Q, you'll know what the total Q is that has flowed past a certain point. So in plain English, you guys, delta Q has flowed past a particular cross-sectional area of a conductor. past the particular cross-sectional area of the conductor, that cross-sectional area is capital A. Delta Q amount of charge has flowed past there in a time delta T. Well, delta Q has flowed past, again, the cross-sectional area, which is A, and how much charge has flowed past there. Here they're just asking you how much charge has flowed past there. Well, N is equal to the number of, N is the number of free charge carriers that could flow, and this is, V is the volume per unit volume, per particular volume. Number of free charge carriers in a particular volume, number of free charge carriers in a particular volume divided by the volume will tell you what N is. Well, if that's the case, number of free charge carriers per unit volume, or just per volume, you don't have to say unit volume necessarily, number of charge carriers per volume times A dx, which is actually the volume. A dx is the volume. Charge carriers per volume times the volume is the charge carrier, number of charge carriers, times the amount of charge on each charge carrier. That tells you the total charge. Well, they got a way of looking at this and maybe saying a little different. They're saying, okay, you could take delta Q, you got N here, you got A, delta X is the drift velocity times delta T. This drift velocity times delta T is equal to that dx. So they're the same thing. Times Q. Well, that's of interest. If there's a drift velocity over a time delta T, delta X of distance has been traversed by charge carriers. In other words, by each, on average, by each and every charge carrier that's present, on average, each one is going on average V sub D times delta T for the time. Each one has gone an amount delta X during that period of consideration. Well, if that's the case, when we're doing this stuff, if that's the case, what we have here, the current, there's a lot of ways it gets talked about. The current is the limit as delta T goes to 0, becomes a calculus problem. We're not familiar with that. We don't need to be afraid of it. Say that the limit as delta T goes to 0, what's the ratio delta Q over delta T? And then that's really the first derivative, first time derivative with respect to dq, with respect to Q rather, and we end up getting, well, I mean, this is very interesting in its own right. If you just divide by delta T on each side, at the end of the day, you got delta T, you got delta Q over delta T, you got N A V sub D times Q. Obviously, you know, people can put this in different places, you guys, when we're doing this. You can put, I mean, doesn't really, here's the thing. In a sense, the delta Q is already out of there. You're not, the limit as delta Q goes to 0. Yeah, there's a lot of ways we can argue this, but for our purposes right here, it's a done deal. It doesn't matter what delta Q and delta T you're talking about. This is what we're looking at. You can rearrange this a little bit, and you end up getting, you just put the Q in front of the N. None of this is essentially set in stone, you guys, to actually get it like that. And you're getting something, and they do say a whole bunch of stuff here. In fact, I wrote it differently than I actually wrote it in my notes. That doesn't, at the end of the day, what does that mean? Well, you got You got the I, and you got this, and I guess we can clean it up a little bit, at least follow some of the ways that at least I saw it in the book. Not that it means anything different, guys. It's the same answer at the end of all this. I is NQ, that's what I moved that. The V sub D is here, and the A is here. That doesn't really matter. It's not a big deal. We're talking about that. And I kind of, I put some Roman numerals on this thing just to kind of have this thing under control. We're going through some of these, but again, the numbers are not, the Roman numerals are not something set in stone, you guys. So we're looking at something like this. So as we go further, let's go to 2. And I talked about a couple things. Now here's, I went through this a number of different ways here. Let me kind of just jump, we're going to use, I'll jump over to this handout, and a lot of this handout is already here, but some of it is not. So I'll probably have them combined at some level, or at least have one follow the other when we look at this stuff to get an idea of what we're doing. So let me kind of use much of what's happening here, you guys, and so I'm going to use, they say some stuff, I'll say some stuff, and then I guess we'll say some stuff again. For number 2, they talk about RC circuits, and tau is equal to RC, and then they talk about 2 different scenarios that can occur. You could be charging a capacitor, or you could be discharging a capacitor. So let's talk about that. And like I said, probably at some level, I think when I'm doing this, I'll have to jump around between the two handouts. But let's do a couple things here. Okay. Let's say a couple things here, guys. I've gone into and again, so especially for the calc-based, for the people that have a calculus basis and are taking a calc-based course, this should be pretty useful. But even without the calculus base to this, there's a lot of the mathematics that won't involve the calculus, but some does, obviously. So again, the conclusions that are drawn are very, very useful to us, though. So let's take a look at that. RC circuits, and I guess the conclusions are probably a good way to go, and then maybe we'll do some other stuff as well. There's a lot of math that we've already done, that you've seen me do before in class, and this is just a summary of what has happened. You got charging a capacitor. Just discharging a capacitor. So okay, so discharging a capacitor, charging a capacitor, let's see what's going on. Well, we were talking about the capacitor problem earlier, and we're going to talk about this in more detail a little bit later. In this case, small q is variable. In this case, capital Q is not variable. It's a constant. It would be Q max is what it is. Later on, I actually label it Q max. Later on, the capital Q, that symbolism actually means, oh, capital Q is a variable and Q max is a constant. So forgive the inconsistency, guys. Let's just try to let's just look at this in the context of that kind of consistency. Charging a capacitor, Q is a variable quantity, small q is a variable quantity, capital Q is a constant. And what we have here is and again, kind of, I don't know if I'd want this standing above this, but just for the record, later on, we're going to be able to verify that tau is equal to RC. So this RC is actually a tau, it's a time constant. So you're looking at this, and at the end of the day, for current, you got capital Q over RC. This is a constant. This is the max current. And I equals E over R over tau. I'm kind of running out of room, you guys. The I max, I equals I max so that's for real. That works. And I don't want to draw too many figures on this, guys. So we're looking at this, and this is the I equal I max, and this is the Q. Here's I, here's Q, and this will become more significant. It'll be seen, the significance will be seen a little bit later. We look at this in a little more detail. Right now, I just want to give the conclusions that we had drawn at some point or another. For discharging, Q equals capital Q, and capital Q in this discussion, this particular discussion right now, capital Q means maximum, Q max. And it's looking a lot like stuff we've done already. Only here there's a negative sign in front. Everything else is the same though. It's kind of except for that negative symbol, everything is the same. This right here and this right here are identical absolute value always. Always. Yeah, and the tau is the RC. Forgive me, guys. Let me stay some level of consistency with this, at least with prior notation. So, okay, you've seen this. Those who are like physically in my class this particular semester, you've seen me do this. So on and so forth on this. So we come back to here. Look at the answer here. That right there and that right there are identical. This has a positive sign in front of it. The right side is 1 times this. And here the right side is -1 times this. It's the same this. They always have the same absolute value. Discharging means negative in this case, and positive means it's charging. So when it's charging, there's a positive sign for the current, and when it's discharging, there's a negative sign for the current, but look at them. They are identical. They're identical in terms of magnitude, rather, I should say. The other ones, there's a bit of a difference, but even here the difference is not as much as you might think it is. The crazy thing is, if you were to add this top one with this top one, the Q e to the negative t over RC and the negative Q e to the negative t over RC cancel when you add them, and you just get 1 times capital Q. It is understood that when you add those two, you're getting the total current that is, you're getting the total amount of charge that is available in the system, that is present in the system. All right, guys. Like I said, they go into that. There's different books go into it and stuff. Let me go to the second, or the second of the handouts, or the second of the PDF documents, or at least called the other of the PDF documents, of these 2 PDF documents that we have. Let me go to the second one here, and let's just let's explore this a little bit, see that this is true, and also go into RL circuits. Now later on we go into RL circuits in a different way. Not quite, so let's kind of see what we can say. So let's stay with this as it is, but let's say a few things about it, and then let's go into the RL circuits as well. I have already gone into this in person in lectures, and I've gone into it to a relatively decent degree in a handout that I gave. Especially when we went into the RL circuit, I went into that the same way I'm going to go into that here. So there's other handouts, and other instances where this content has been covered, in handouts and in lectures, let alone the fact that's in the book as well, okay? So let's take a look at some of this stuff, you guys. Let's deal with the RC and RL circuits. Okay, some kind of sense of what's happening. Okay. We've said some things, as I said, even very recently in this video, and like I said, those who have had me as their teacher in other circumstances, we've said this in person and in writing. Let's kind of go somewhat rigorously into some of this stuff. Let's talk about Q of T for a charging capacitor. Well, I mean, the Katz book was consulted significantly on this. Dr. Deborah Katz's brilliant work in her elementary physics book was consulted on this significantly. So let's look at that. So that's a great reference, Dr. Katz's book. In elementary physics, basic electricity and magnetism calculus treatment of the subject matter. Well, let's see a few things, if possible. If there is a power source, positive, negative, capacitance C, resistance R, electromotive force, potential difference, however you wish to call it, E, and you're looking at this, and we're looking at summing all the potential differences, as we always do, and see what sort of behavior can occur. Let's see what conclusions we can draw. Well, if I sum all the potential drops, they're going to add up to 0. Good enough for me. Now what? Well, E is E. There's a drop right here as we go through the resistor, and there's a drop associated with the capacitor. Now let's be careful with that. Delta V for the capacitor at any particular instance, I guess you could say, is Q over C, because C is equal to Q over delta V. Multiply by delta V on each side and divide by C. And that's where that's coming from for the capacitor. So it's looking like that. Well, let's see. I mean, there are things we can do to make this work out. What do you say you multiply by C on both sides? Well, time out a second here. Here we get a little bit into calculus. Now those who are watching this film's intended for, I guess, all audiences with all mathematical backgrounds, provided we have a relatively strong basis in somewhat more complicated, somewhat more advanced algebra at the very least, and then calculus as well. I mean, the calculus background is ideal. You don't have to get everything that I'm doing when I'm doing a lot of these videos if I'm giving it to an audience that may have a calculus background, may not have a calculus background. The conclusions that we draw are really the main thing that we're concerned about when you're actually doing particular problems. You're usually not being asked to prove something at that point. With that in mind, you're going to multiply by C on each side, but before you multiply by C on each side, I is dq dt. It's delta Q over delta T, or in calculus language, dq dt. R is R, multiplied by C on each side. When you multiply by C on each side here, well, you just multiply by C all the way across on each side. I is dq dt. And we've gone there. I is delta Q divided by delta T, which is the same as I equals dq dt, if you want to go into the calculus realm. So we're looking at this situation, you guys. Now, I just made one mistake here. I shouldn't have made. These are potential drops when this happens. Forgive me. Potential drop here. Potential, so these are all potential drops that occurred. All right. As it was going, it starts with this, and every one of these takes a piece of it. So it's a subtraction on both sides, in both instances there. Take dq dt RC and add it to each side of the equation, and you end up getting this. Dq dt RC, add a positive dq dt RC on each side, and it's going to be equal to true. Divide by RC on each side. Okay. Multiply by dt on each side, and divide by the quantity EC minus Q on each side. So you end up getting and you got dt here. It's looking like that. Well, once you get to here, I mean, I don't want to, beat this up too badly, guys, but I want at least, like I said, for those with the calc background, you've probably seen it. If you've not seen it, you're going to see it now. Those without the calc background, we'll at least make a few moves to get us to a place where algebra can get us done with the rest of the stuff that we got to do. So, I'm going to integrate both sides. I'm going to go from no charge on the capacitor to Q amount of charge on the capacitor. And I'm going to go from starting at time t equals 0, going to a time t equals t. Well, sounds good to me. If you do this is kind of like a famous integral, so to speak. The integration of 1 over something pertains to the logarithmic function. But you got to be really careful how it pertains to it. It's negative ln, because there's a negative right here. It's a negative ln EC minus Q. Yeah, and that should be okay. Put a negative 1 right in front of it if you want. Maybe it makes it a little more rigorous. And this is evaluated. Now, this is where the calculus comes in, guys. If you don't have this background, don't worry about it. We're going to get away. We're going to work this thing, derive what we need to derive, then we're going to get down to some algebra, and you will know enough algebra to finish this. So you look at it, same thing here. The integral is just t over RC. Between these limits, 0 and t, that's just that. This right here can be a mess. Let's deal with it. You basically got -1. It's going to occur in both places. You got ln EC minus Q. That's what that is. And the other one is minus ln EC minus Q, and the Q is equal to 0, so it's just that. And this guy's T over RC. Well, the rest of this is essentially a non-calculus problem. Now, if you're willing to take it on faith that we got that we're able to get to here. If we're able to get to here, what can we do? Well, hopefully we can get out of this thing okay. I mean, there's a lot going on here. I got two sides of, there's two sides of the equation, and it's indeed an equation. That means the left-hand side is equal to the right-hand side. I'm not saying anything too profound. If these two things are equal to one another, you can divide by -1 on each side, or you can multiply by -1 on each side to get the negative out of there. Well, okay, let's go. I'm going to multiply by -1 on each side and get this. Right? Equals -t over RC. I just want to make sure you guys can see that if it's in my film. Yeah, it's not great, but it's there. You can see it. I'll make it more clear in a second, guys. So what we have here is, come down to there. What is the difference of two logarithms? It's not the ratio of logarithms, it's the ratio of the arguments. It's, the difference of two logarithms. And here we are, there's the difference. The difference of two logarithms is not the ratio of logarithms, it's the logarithm of the ratio. The difference of two logarithms is the logarithm of the ratio of their arguments. In plain English, the difference of two logarithms is the logarithm of the ratio. Okay, pretty interesting. What do you say, if they're both equal to each other, what do you say you exponentiate? If two things are equal to each other, then when they're both exponentiated, they're still equal to each other. Put this on top of E. That and that. And you're going to put them both on top of E. Put this on top of E, put that on top of E. Put this on top of E, put that on top of E, like I did right here. The exponentiation of the logarithm of something is just the something. And the exponentiation of this is what it is. So, sorry guys, I'll get better erasers next time. I kind of got into this a little bit at the last minute. But at least you guys got the reverse feature, so you can see what is already on, what's already been on the board. That makes things somewhat easier. See where we can go with this thing. See where we can take it. Okay. Once again, this left-hand side equals that right-hand side. Then this can be put on top of E, and that can be put on top of E, and whatever happens, it's still an equation. The exponentiation of the logarithm of a quantity is the quantity. The exponentiation of the logarithm of some quantity is that some quantity. What does that mean? It means basically let's have a look, guys. Well, there's a lot going on. I mean, let me okay, the order of this is rather interesting. Okay, guys, let's see what we can say here. Have to look a little bit at the ordering of this. Okay, so I went and did a lot of stuff here, but okay, it all comes, kind of comes around full circle. Basically, you go here, and what you got is you got a few things kind of in the back of your mind here. Now, later on, big Q is going to be a variable in some of the work that we do. It's going to be a variable. Here it's not, it's a constant. It's equal to Q max. Right here in this, in this part of the discussion, Q equals maximum charge. So C equals Q over E. Q equals CE. Tau equals RC. Well, this we know. We've seen this. We've dealt with this in various discussions. See where this goes, guys. It's essentially coming to EC minus Q over EC. That we just said that the exponentiation. What I had done here, guys, I had come. It's kind of a weird questioning my own way of approaching this whole thing, I guess you could say. Yeah, there's different things that come into play here, and right, some of the ordering here is a little rather interesting, but we'll figure it out. EC minus Q over EC equals multiplied by EC on each side That right there is the Q max. That right there is the Q max. Add small q on each side. Add a small q on each side. You can cancel the negative q. Add a small q on each side. You can cancel the negative small q. And subtract big Q e to the negative t over RC on each side. So you end up getting you come to here, and there's more to do. Take the big Q out of there. And that's where they're coming with that. So that is for charging a capacitor. I'd gone into I'll see what I can do as I'm looking at this right now, you guys, how I can maybe handle this. So we'll see how it works here. I think there's a little shorter. But this is fine. There's nothing wrong with this, but I guess some of the order in which this is to be found. All right, so. Okay, so you're looking at this. What can you say? Well, can you say anything more than this? Okay, we got that. Okay, some of the ordering here, guys, I might have to do a little bit of work on it, how this thing is ordered, but for our purposes, we're fine. Yeah, we know I of t is just I. That's dq dt. dq dt is the time derivative of this. And it's a bit of a mess when it happens, but if you do take the time derivative of this, you can kind of look at this one, maybe a little easier to look at, before you factor the q out. Minus q e to the negative t over rc minus q e to the negative t over rc is the same as plus a negative q e to the negative t over rc. So, not bad. If you take a time derivative here, this constant, the derivative of a constant, time derivative of a constant is 0. The time derivative of this is negative q e to the negative t over rc times, by the chain rule, negative 1 over rc. So negative q times negative 1 over rc is positive q over rc, and that's kind of where it's coming from, guys. So it's positive q over rc, pretty fascinating stuff. That's negative t over rc. C is capital Q over the maximum potential difference, Q over V. This is Q over V. Q over V goes into Q times, and then V flips upward, and it becomes, well, look at it. This is Q over V. Q over V, the Q's cancel, the V flips upward. It's V divided by R, maximum potential difference divided by R. That's equal to maximum current. That's equal to maximum current yeah, I mean, so there you go. I mean, that's where it's going in that regard. Again, this is, sometimes just you want to unify and keep it in one place when you're talking about it. For the charging of a capacitor, and like I said, it's, this whole thing plays out a bunch of ways. We kind of did that earlier. Well, we did it earlier, and I unfortunately ended up erasing it. But, Q over RC is equal to I max. There's a lot going on there. I mean, this right here, the EC, that's capital Q divided by E. I mean, that big V I used earlier, guys, probably more realistically or more in line with the original assumption, that capital V, that V max, the delta V max, that's that E right there. So that's, it's a horse apiece. Just watch out though. Make sure we're under control when we do this. Okay. That's it. I mean, there's a number, again, you'll see it in the notes in a lot more detail. But here's Q, small q, which is a variable quantity. This is Q here. Over RC, or over tau. There's so many symbols here, guys. I guess we have to, we got to be careful. We need to kind of keep track of what is what. But there's Q, and here's dq dt in that process. And this, and that's for the charging, and that's for a charging capacitor. Charging of a capacitor for the charging, for charging capacitor, okay? So for discharging capacitor, what's going on? Well, it's very much of the same argument, just got to be careful. So that was for a charging capacitor. That's what we started with, and that's what we got. Let's erase some of this stuff and see what we can say. Okay. For discharging capacitor, how are we gonna figure this one out? Well, you're not gonna put. It's kind of a little bit of an awkward thing. When we were charging up the capacitor, we needed a power source to get the capacitor all charged up, and we drew the conclusions that we drew. Yeah, absolutely. We drew the conclusions that we drew. Now, once you've completely charged up a capacitor, you can disconnect it from the power source, disconnect it from everything for a while, and then somehow, seamlessly, if it can be done, you reconnect it to a resistor. So it's just an RC circuit there's no battery this time, and you're discharging the thing, and you see how it behaves in the discharge. You've already charged up the capacitor as far as the battery of potential difference E can give you. So I'm going to use that E in some of the mathematics, even though the battery is no longer connected. The battery did its job. It charged the capacitor as far as it can go, and there's no more flow of anything right now, no more flow of current. So when you disconnect the battery and make sure that there's no way that there's any flow away from the capacitor until you want it to happen, you attach a switch to it, then you'll see what happens. We know it took potential difference E to get it to a maximum charge of capital Q. Later on, capital Q, I'm going to use it as a variable, and I'm going to write Q max for the constant. But here, right now, so far in our discussion for the last, last period of time that we've been talking about some of this stuff, charging up a capacitor, now discharging a capacitor, capital Q is going to be a constant. It's going to be Q max. Later on, I'm going to have to say Q max explicitly because capital Q by itself is actually going to be a variable. For right now, the variable that I'm using is just small q, okay? Well, things already been charged up, you guys. So let's see what we can say here about this. For discharging a capacitor, let's be careful with the language. It's always, I frequently, at least according to my memory, and that doesn't mean I can remember this perfectly, but it seems like in numerous places, the discharging of the capacitor doesn't always get discussed very much. Perhaps it doesn't, perhaps I just can't remember it right, but it seems like in some instances, the charging up of the capacitor is sort of an easier conceptualization and an easier explanation than that can maybe happen when you're talking about discharging a capacitor. So let's be careful here. And I think I believe that to be true, that it's an easier explanation to talk about charging a capacitor than it is to talk about discharging a capacitor. That's my belief, that's my opinion. I'll tell you what I'm going to do. Once you're going to discharge the capacitor, let's say Q prime is amount of charge remaining on capacitor at time t. What does that mean? Well, that means when you started the whole process, didn't we say you basically took it to the limit? You put capital Q max on there. And again, we're calling capital Q max just capital Q. Just now. Later on, it's going to be different, as I said. But we're going to say capital Q is what's on the capacitor when you don't do anything to it. Capital Q is what's on the capacitor, and if you subtract Q that leaves the capacitor, you've got Q prime. So, amount that left, take it away from what was on there. This is the maximum amount. This is the Q. Big Q is the maximum amount that could possibly be there. The amount that is left at time t, take away from capital Q, will leave what is left on the capacitor. That's Q prime. We're going to solve for Q prime, but when it's convenient, we're just going to rename Q prime Q. This is why this is kind of a hard one to discuss sometimes. The language of it gets to be a little bit of a problem. Well, Q is C times E, based on past conversation, and at any particular time during this process, what is the potential difference across the capacitor? The capacitor starts behaving like a battery in a sense. At a particular, but it's not a battery with a constant E. Its potential difference gets smaller and smaller as charge is discharged from it into the circuit. So if that's the case, and there's a lot of oscillation that takes place, they didn't really go there with that, and some of the discussion we had done in some of the books I've looked at, so we're not going to, some books talk about it, some books don't. For what we're doing now, especially for the non-calc based class, they didn't really go there, so I'm not really going to go there right now. But let's take a look at it. There's got to be something here. Actually, I'm just going to have to take that back. At least some of that's got to be taken back. You look at this. No, we're fine. We're fine. There's a little more to this than potentially can meet the eye, and I'm gonna go into that in another kind of a problem when I talk about the inductor capacitor circuit, the LC circuit, which should be really interesting, and that talks about an oscillation. In this circumstance, there's also oscillation that takes place, but the resistor does dissipate a lot of what goes on. So you look at it, the resistor will do something. There's probably a number of ways we could look at that. Much of the discussion has not gone in that direction, so I'm not going to go in that direction right now either. I'm just going to say that capital Q is C times E. The capacitor charge divided by C is potential difference. That's the amount of potential difference that is there. At any particular time, it'll get up there and it'll do it again, I guess you could say. But let me try to think here, guys, exactly how you want to look at this. Right, so let's just stay here, and let me go minus IR equals 0. Probably a number of ways we can look at this and a number of scenarios we can construct with their own kind of fascinating equations. Let's us stay here. Let's us just say, look, this thing is going to go all the way around here, and in aggregate, what's going to happen? In aggregate, what's going to happen? Well, there is going to be oscillation. I can practically guarantee that, but they're not going there, so we're not going to go there right now either. We're going to say, okay, let's let this thing just go all the way around here, and let's see what we can do. The oscillation will be damped because there is a resistor there, so it's just not going to go forever. I'll give you a situation where it does go forever, theoretically, much like a spring with a mass on it, an ideal spring with a mass on it on a frictionless surface, how it'll oscillate back and forth with no loss in energy. The LC circuit will tell us this. For right now, let's just stay with this, guys. Let's stay right here. V minus IR, this is V. This is kind of like the potential difference. Minus IR equals 0. Let me see if there's something I can say here. Well, according to their argument, they take a look at the I, and that's dq dt. And here we go again. dq dt RC. Well, there's a lot. They're doing a lot here. If they're doing a lot, I'm going to do a lot. At least what I had done earlier, let me kind of make some sense out of this thing. Let me leave this IR equals 0 right here. Sorry about that. And I is equal to dq dt, so let's go over here. Q over C minus dq dt times R equals 0. That's for one move. The situation is, just trying to think here, guys. There's a lot that can go on, I guess. But this is just for one move, I guess, to make this all happen. Let me see what we can do here. All right. We've got this right here, multiplied by C on each side. Multiply by positive dq dt RC. I'm sorry, forgive me. Add a positive dq dt RC on each side. That negative goes. Let's multiply by dt on each side. Let's divide by the quantity capital Q minus small q on each side and divide by RC on each side as well. So we can kind of look at this. Let me just kind of see where we are at. There's much can be said. I don't think it needs to be said right now. Let's just stay with the problem as it is. We got this right here. And if you integrate this and you want to say, well, how's this all going to go? What are we talking about as this thing's discharging for a given circumstance? We are looking at a situation where, okay, so I'm going to do the integral here. Here we go again. Well, we don't, 0 to some q, that's going to be left there, right, of dq over capital Q minus q equals the integral dt RC over some. So it's pretty fascinating stuff. On a number of levels, you guys, as this thing proceeds. I mean, it's going to come out. Just try to figure out exactly where it's going to come out. Yeah, this is fine. This is all fine. Well, keep going. I mean, you do the whole song and dance we did earlier. It should look a lot like everything we've done. I mean, this right here is the telltale sign of something moving, something involving the logarithmic function. This, at the end of the whole day, is going to be that. Here we go again. We got this. We've got ln start at a particular q minus ln. Put a 0 right here. There's your capital Q. So you got that. That looks awfully familiar and yet at the same time different from stuff that we've done elsewhere. So you look at it, multiply by a -1 on each side, multiply by a -1 on each side of the equation. You get a negative t over RC. The negative's no longer there. The difference of two logarithms is the logarithm of the quotient. So now here we don't have to have calculus. So far so good, actually. I mean, the Q prime is equal to that, so I think we're looking pretty good. We got to do something here. We did what we did. Now this right here, a lot of ways to go here. Let me see where we want to go here. Let me stay with this as is. So we got this. You guys all got this. Everybody's got this. If these two are equal, we just said they're equal to each other. They're equal to each other. If they're equal to each other, if you put both of them on top of E, both of them on top of E, we end up getting guys, not the greatest drawing in the world here on my part. That's E, that's E. Exponentiate both sides, you got this. Now we got to do a timeout for a second. This is Q max. What is that? It's Q prime. Q prime is the amount that's left on the plates. Q prime is the amount that's left on the plates as this is taking place. So a lot of arguments can be made. We're not going to make all the arguments that can be made. For our purposes, this is the amount of charge left on the plates after a time t. Period. For our purposes. We're not going to look too much beyond that. That's the amount of charge left. Q prime is the amount of charge left. At this point, you guys, and only at this point, you can call Q prime Q, call it Q, and Q is the amount of charge left on the plate. And that's where they're doing. So it gets a little, I know students of mine have rightfully said it is confusing. It is rather confusing. Maybe they should have gone with the Q prime from the beginning when they're discussing this stuff. They're trying to derive this stuff or discuss this stuff. Maybe go with the Q prime from the beginning. If you take, so that's that. I mean, you got that. The I is dq dt is equal to Q e to the negative t over RC times negative 1 over RC Q over C is V, V over R, or Q, Q over C, C is Q over E, which is the delta V max, becomes E over R. As this thing is discharging. This is one cycle. If it discharges completely, you guys, it's pretty interesting how that all works out. I mean, in its own right, you guys, if it discharges completely, how does that work? Is it going to cycle back and forth? Yeah, there should be some tamping that takes place. There should be some damping that takes place. But anyway, for our purposes right now, this is one shot where the whole thing empties out. One cycle, the thing just empty, or at least, the capacitor is fully charged and it becomes, all of what was originally there leaves. And where does it go? Well, yeah, a lot of it goes back to the capacitor, but a lot of it's been dissipated because of the resistor. That discussion's not really been brought up in much of the conversation that we've done at this level, so we're not going to bring it up now either. I mean, at least excessively. There should be some value, some measure of oscillation at that point, though. This is I equals, and we'll definitely see oscillation in a little bit. You got this right here. So you got I equals I max. You know what I max is. I mean, I max is going to be E over R, is going to be Q over RC is I max, E over R is I max. The negatives here, though, when you do the derivative, you end up getting this times, right, a negative 1 over RC times that becomes all that. So, and you end up getting this. The RC is tau. So this is for a discharging capacitor. Interesting. What had we done? I mean, what have we done here? For the charging capacitor, I was about to write it another way, and that other way works, but this is a better way. Pretty fascinating stuff. Forgive me, guys. It's a negative. That's a negative. And this is one-time emptying of it. How does it behave this one time as it goes through the resistor? This is just discharging, this is charging. for charging, for discharging. Forgive that negative, guys, but it's got to be there. And it's faithful to what's happened. This is a one-time. I don't know what we can look at and look at various assumptions of what is going on and how it's going on, but we will look at a one-time deal of this thing discharging. One time, completely discharging. How is it behaving at any particular period of time t? How is it behaving when it's discharging? This is how it's behaving when it's discharging, and this small q is the amount of charge at any time t that is left on the capacitor as the discharging is taking place. I know when I was doing the mathematics, it was actually, that q was actually the q that was leaving. Earlier when we were doing the mathematics, this is the q that's leaving. One-time deal. I'm not going to talk about some oscillation taking place. I'm going to talk about a one-time deal. This thing's going to go around, discharge, and while it's discharging, what is the behavior of the charge on the capacitor? How much charge is on the capacitor at a time t while this thing's discharging and it's going through a resistor? What's the charge Q that's on the capacitor as this thing's discharging? Well, the charge Q that's on the capacitor when this thing is discharging is really the Q prime. When we solved it for Q prime, and then we said, okay, now just call the Q prime Q, and that Q is what's on the capacitor at a time t as, forgive me, right here, when it was discharging. This charge Q prime, we just arbitrarily called it Q just to be easier to look at, I guess you could say. But it was really, Q is really what's leaving the capacitor when it's discharging. Q is really what's leaving the capacitor when it's discharging. Q prime is what's left on it. When we solved it, we actually solved for capital Q minus small q. That's what's on it. That's Q prime. This capital Q minus small q, we'll just call it Q. There's Q amount of charge on the capacitor at time t as the capacitor is discharging in this first round. I'm not going to talk about any oscillation. None of our business right now. Just this one round that it's doing, how's it behaving? Well, I got this. This is the amount of charge. This is the amount of charge that's actually on the capacitor. This is the amount of charge that's actually on the capacitor as it's leaving. Forgive me. This is the amount of charge on the capacitor as charge is leaving. What is that? That's Q prime. That's really what it is. That's really what's on the capacitor. So what would happen if you would have gone dq prime dt? You'd have gotten a positive. You got an I. The amount leaving would be positive, would be I, the amount leaving would be I equals positive I max e to the negative t rx, e to the negative t over rc. If you were talking about, you had it to here, that was the Q prime. That was Q prime. If you were saying this guy at the end of all that day was equal to this, and that's what we did earlier, if you take the derivative of this quantity, you end up getting, derivative of this with respect to time, whatever it may be, it's an awkward looking thing. Leave it alone, and you end up getting negative 1 over RC Q e to the negative t over RC. Yeah, that's true, but by the sum rule, d big Q dt is 0, and this is negative dq dt. So this would be negative dq dt. That is, if you multiplied by negative 1 on each side, the dq dt would be the stuff being expelled. And it's being expelled at a positive rate, you guys. That Q over RC, it wouldn't be a negative Q, it'd be positive. It'd be positive Q over RC. That would be a positive number. This would be indicative of what's the rate of the charge leaving. What's the current of the charge leaving? Oh, it is equal to that. What's the rate of the charge staying, however? The rate of the charge staying is actually this. The amount staying is less. You know, the rate at which something stays is if it's this much leaving, the rate at which something stays there is the opposite of the rate of leaving. So it becomes that. This is really the dq prime dt. All right, but forgive all the wordiness, guys. You know, it's stay where you're at. I mean, we made a move after we had this guy as q prime right here. We said, you know what? We know it's the one that stays. Let's say this is the rate of staying. Well, the rate of staying, or the rate of something going on, at what rate is this Q increasing? Well, it's not increasing. Why? Because charge is leaving the capacitor. How could it increase? Therefore, it's negative. And it's manifest even in the mathematics. So this is where it's at. I mean, this is the whole thing, guys. So you see, when you're talking about charging, talk about charge, you know, here's if you charge a capacitor, here's if you discharge it. Okay, some of the mathematics that come into play. All right, guys. When we look at that, and again, there's a whole, and that's everything I've been basically trying to say here. They talk about the RL circuit, and let's just talk about that a little bit. You're going to see some of the similarity. Again, this lends itself a lot better when we're all together in person talking about this kind of stuff, you guys. But this is actually where it's at. It's actually where it's at when we're doing something like this. Okay. Charging, discharging. Of course, it's going to be a negative current flow because how much is getting onto the plate? Well, nothing's getting onto the plate. It's actually leaving the plate. It's a positive amount leaving the plate. And how much is getting onto the plate? There's no getting onto the plate. It's leaving the plate. It's losing. So, of course, it's going to be a negative. And the mathematics is indicative of it. So, what we can say here, have some better erasers, hopefully, guys, or at least a little more. Better cover for this stuff. Down the road, I have a little bit better eraser for us, I think. See what we can do now. Okay. So for the RL circuit, you guys, talk about a number of things here, and I was putting the carriage in front of the horse on some of this stuff. Yeah, let me see here. All right, well, you have a little bit of the carriage in front of the horse on some of this stuff, guys, but let me just, let's get through this part of this, I guess, and I think it'll help us out, I guess. Okay, much the same argument, and at the end of all this, not only is it much the same argument, but you're gonna see much of the conclusions look very similar, I guess you could say, when we talk about the RL circuits. Let's take a look at that. RL circuit. Let's talk about potential differences. E is equal to E. Delta VR equals negative IR. That's the potential drop. And dVL associated with the inductor is associated with the potential drop when something tries to get through the inductor initially and there's a change in current. There's an abrupt change in current, either gaining or losing from the initial current under consideration. When you're using calculus on this, if you're going to add these all together, you're going to add them up all together, you're looking at stuff we've done in the past. The symbolism's a little different because the mathematical, some of the physical properties are different that we're talking about. Rather than, let's use some calculus again. This is delta I, this is delta T. This is delta I, this is delta T. And you don't have to know calculus, guys. At the end, if you're not in a calculus-based class of mine, just know the conclusions, be able to do the algebra that pertains to it. That you have to know. Okay? You're looking at something like this, and here we go. We're going to try to solve for I. We're going to try to do a whole bunch of stuff. So, why don't you get L di dt all by itself? Why don't you add it over to this side? Well, if you add it over to that side, just kind of like flip the thing around, just so we have the L di dt all by itself on the left side. But here I'm going to put it on the right side initially. I'm going to add a positive L di dt. I'm going to add a positive L di dt on each side. And you got this right here. I'm going to multiply by dt on each side. This is looking very familiar. And absolutely. And then what you can do is divide by the quantity E minus IR on each side, and also divide by L on each side. sure looking kind of familiar. I mean, at least the structure of the mathematics looks similar to stuff we've done in the past. Tell you what, you got it down to here. I'm going to do an integral. You don't have to know how to do this, but when I'm done with the calculus, you got to know how to do that. I'm going to integrate from 0 to I. Sorry about that. I'm going to integrate from 0 to I. I'm going to integrate from 0 to t in the appropriate spots. So what we have here is here we go. It's a lot like the logarithmic function again. -1 ln of, well, you got to be careful on this one because there's more, a little more that meets the eye on this one. But it is a logarithmic type function. The integral results in a logarithmic function of some sort. The integral results in some sort of logarithmic function. What is it? Well, it's going to be ln -1 over r. If you were to differentiate this, you'd get back to this, 1 over the quantity e minus ir. It's a bit of a mess, but it works. You get to here. Do this integral. Get t over L evaluated between t equals 0 and t equals t. That's just going to be t over L. Do this right here. Here we go. Negative IR, leave it alone. Put it out there. Do the evaluation here. Multiply by negative r on each side. Let's do it again. Multiply by negative r on each side. If you multiply by negative r here, you get 1 in front of this. Multiply by negative r here, the difference of two logarithms is the logarithm of the ratio. The difference of two logarithms is the logarithm of the ratio. This right here, you're going to have to trust me on this one, guys. We'll put a negative right here, and we'll flip the r over L to L over R. And just like tau was equal to RC for the RC circuit, tau equals L over R for the LR circuit. Earlier we said that tau was equal to RC when we were dealing with a capacitor that was charging or discharging, and there was a resistance present. With a resistance present, and I didn't talk about subsequent things that happen if oscillations will occur, and they will, and they can. We didn't say anything like that. We just said one-time deal, what happens? Let's do an equation for it. We did it. We're essentially doing the same thing here. Tau was equal to RC. Tau was equal to RC when we talked about the RC circuit. A capacitor and resistor in a series circuit, and how the charging and discharging of the capacitor took place. Now, when we talk about an inductor and how magnetic energy is stored or dissipated in an inductor, what's going on? Well, tau was RC for the RC circuit, and tau is L over R for the LR circuit. So we got this. And this guy's equal to tau, as we said. There's tau. Well, let's talk. I mean, well, let's deal with it, guys. If those two items are equal to each other on the far right-hand side, lower part, if ln of the quantity E minus IR over E is equal to negative T over the quantity L over R, if they're equal to each other, if you were to exponentiate each side, I'll put a tau here. Tau is going to be L over R, rather. That's the tau. It's going to be L over R. So let's see what we have here. The exponentiation of the logarithm of something is the something. The exponentiation of this is what you have. And that's R, the tau is L over R. Okay, multiply by E on each side. Really looking familiar. It's like charging up a capacitor, isn't it? Multiply by E on each side, and you end up getting T over tau. The tau is not RC now, it's L over R. Add a positive IR on each side and subtract E times E to the negative T over tau on each side. And then rearrange it, get whatever the answer is going to be over the other side. So you can do that, and what you can do is divide by R on each side. Well, that's pretty famous already. I mean, E over R is the potential difference. It's the maximum potential difference that could occur. It's looking something like that. Okay, did I just erase something I didn't want to erase? I don't think I did, but E over R is I max. There's a number of ways to go, but in the end, you're going to the same place, you guys, and that's what we got right here. Looks a whole lot like Q equals Q max times the quantity 1 minus e to the negative t over the tau pertaining to the capacitor and to the resistor. So, pretty fascinating stuff as this is actually taking place. Looks a lot like you're basically loading up an inductor. You're loading up an inductor to a maximum amount of potential energy that it can have, of magnetic energy that it can have. You're loading up the inductor and you're doing it with current. Whereas with a capacitor, you're loading up the capacitor, charging the capacitor with charge. You're empowering the inductor, I guess you could say. You're loading up the magnetic energy associated with the inductor by running current through it. The same way, in an analogous way, that you're charging a capacitor by putting charge on it. Putting charge on a capacitor, you're increasing its potential energy. Putting current through an inductor, you're increasing its potential energy as well. The potential energy associated with the inductor is magnetic energy. The potential energy associated with a capacitor is electrical energy. So, some looks at stuff like that. There is the idea, and again, we're doing a lot of this stuff. We're doing kind of a one-shot deal when we're doing this stuff. There is the idea that there's going to be oscillations, but they tend to get damped, And in an ideal situation, if there's no resistor, the oscillations aren't going to get damped, and that's what we're going to get into at a future time on this. So there is. And we talked about various things. Okay, let's proceed down the road a little bit on this. All right, guys, hello again. I took a little break here just to put some of this stuff up on the board, talk about a few things, and we'll figure out how we want to do this. Regarding some of the review that we can do, look at some of this stuff just to keep in our mind. I can get to topic 3 as well, based on the earlier stuff that I had done. Now, I'd worked, up to this point, we worked through topics or sections 1 and 2, and then some other stuff. We talked about drift speed earlier, and RC circuits. Well, we talked about RC circuits quite a bit, both the charging of a capacitor and the discharging of a capacitor. So that was our discussion on RC circuits. We talked about that quite a bit, and we also talked about RL circuits. when an inductor is present, and how that all works out, and how much of the mathematics was similar. So we talked about things like that, like I said, the drift speed, RC circuits, RL circuits. Let's briefly just look at a few things that we just want to keep in our mind. When we talk about magnetism, force vector equals Q V vector cross B vector. F vector equals F vector equals Q V vector cross B vector. From there, you can derive this pertaining to circuits and magnetic force that's associated with that. F vector equals I L vector cross B vector, and that comes from this very famous, very interesting, very useful fundamental equation related to a charge moving through a magnetic field at a particular angle with a velocity v vector. F vector equals Q times V vector cross B vector. Written without vector notation, if you're really sure where the directions are and everything, you can write it like this. Same with this right here, can be written like that if we're pretty confident what's going on with the direction of the force being applied. Mu, the magnitude of the magnetic moment, NIA, and torque vector is mu vector cross B vector. So we've talked about that. Biot-Savart law, be careful how you remember this. You can remember it a couple different ways, just don't mix and match the way it can be remembered, is what I need to really tell people. It is a wonderful law that tells you where the B field is associated, once again, with a charged particle moving. But in this case, it's a little different dynamic. Here, when we talk, and I can't really, just coming back to this, guys, forgive me, I mean, for magnetism, F vector equals Q V vector cross B vector. A lot of times, to be short, I guess you could just say F equals QV cross B. Very fascinating. It can give you an intuitive look of much of what's going on. Whether we're talking about the flow of current, whether we're talking about, making a derivation of what a generator does, how it does it, what's the mathematics behind what a generator does. This equation, F equals QV cross B, lets you get an intuitive look of what's going on. Gives you a really intuitive look it gives you a very intuitive look regarding flux and regarding Lenz's law pertaining to flux and changing flux. This gives you a very intuitive look as to what goes on if you apply it correctly. If you apply it correctly, it gives you a very intuitive look regarding what happens with flux and changing flux. And the amazing thing is, even when you're not easily able to look at changing flux in terms of something like this, nature behaves as though this formula is happening somehow. If it's changing flux we're talking about, no matter how the flux is changing, we are still getting the answer as though there was some movement through a magnetic field, as though there was some movement through a magnetic field. If the numbers are identical, if the mathematics is identical that we're describing, it doesn't matter how the change in flux is happening. Pretty fascinating matter. So this gives you an intuitive look, and you can see it no matter how the flux is changing, whether it's a changing B field or the changing area in one way or another, or I'm sure there's numerous other situations we can look at as well. Lenz's law holds, and it holds as though the same way it would hold for like a generator whirling around a constant, spinning and being encountered by a constant magnetic field. The constant magnetic field and the generator turning, you could use this formula to really visualize what's happening and get an expression for the induced EMF. Regardless of how it happens, whether it's looking like a generator or something else, if the flux changes in the exact same way across various circumstances, it doesn't matter. The EMF induced is the same. Pretty fascinating. So need to go back to that. This is a little different dynamic. Here, you're not talking about a B field in which something is moving. You're talking about a B field that is actually produced because of the movement of a charge or charges or current in a wire. And B vector equals mu 0 over 4 pi times Q times V vector cross the R vector over R cubed. Well, the R vector, you can make it into, you can describe R vector as R times R unit vector. R vector can be written as R times R unit vector. That's a scalar, that's a vector, it's a unit vector. R vector is R times R unit vector. Well, if you put R times R unit vector here, look what happens. Change this really quickly, and you look at the R vector, and that's R unit vector. The R and the R cubed cancel, and you got this, and that's where you're getting this. And that's where you're getting this. So just be careful. I mean, that's simply, it's simple as that. That's true. So both circumstances are true. Here is R vector. And here's R cubed, and it comes down to here. I mean, I've made mistakes where I've made the assumption that this was R vector. I made the assumption that this R vector was R unit vector, and I think I left R to the third. Well, then I'm off. I mean, the numbers I'm getting are smaller by a factor or whatever they are. They're off by a factor of 1 over R. So just watch out. Be cautious of that. Be cognizant of that. It's a great formula, very useful. And again, this is where you can take it from the particle to the we're talking about a current flowing, similar to what was happening over here, from particle to current flowing. But this is, like I said, this very fundamental formula right here. It gives you some tremendous insight regarding a lot of these matters. So again, very fundamental. Obviously a fundamental formula. There's many fundamental formulas. That's one of them. Here's another one for you. It's identical. These two are identical. And you can write it in terms of, if you know where the B field is going to be, you can do something like this to get down to here. And they're just basically saying if the charge Q were moving in direction of the V vector, Q is moving like this, called V vector, a magnitude V vector in a direction, Q moving according to V vector, and it's R away from here. There is a current in this case. There's like a current in this case. If you do the right hand rule with the current in this case, put your thumb this way, roll your fingers this way, the B field's into the board. That's kind of consistent with what we've talked about in the past. So Q moves according to V vector, moves with a velocity V vector. Q moves with a velocity V vector. It's a distance R vector away from here, and you'll get B vector. You'll get a B vector, whatever they may happen to be. So you'll get a B field right here. You'll get it in other places as well, according to distances involved. According to numerous instances here, guys. You could say here. So theta and phi could be the same. I called it theta in the notes, but it's the same as phi, and we use phi over there. Could potentially be in any direction. So let me write that here, guys. B vector could potentially be in any direction depending on the problem, what's set up here. So we can find out what the B field is right here when Q is doing that. And we sure find out a whole lot of stuff, guys. So the way it comes out here is you would look at You know, you're basically, there's a lot of math to be done when we're doing something like that, obviously, guys, but essentially this is where it's going. When you're looking at something like this, at that particular point, that's the B field. Now, if it's somewhere else, if the charge is over here, you know, the R vector is something different. So you got to keep that in mind. But some wonderful, wonderful mathematics, wonderful formulas there. They are, from what I understand, they're empirically, they are arrived at. It has been seen empirically through experimentation. They've determined that these formulas are valid, and again, some beautiful mathematics and very useful for us. Ampere's law, basically, you know, you're saying, you know, the integral of B vector dot dl equals mu 0 I. B vector dot dl equals mu 0 I. For a wire, this is a very common conclusion associated with Ampere's law. And then if you're talking about two wires that are close to each other, or wherever they are in relation to each other, what's the force between them for a given length, over a given length of time? Now, the wires could be infinitely long. I want to know what the force is over a distance of 10 meters where they're both going together, and they're both, let's say, a meter apart, and over a 10-meter stretch of the flow of current, over that 10-meter stretch, what is the force exerted by one wire on the other? Newton's third law holds, obviously. What one wire exerts on the other, as a force, the other wire also exerts that same force on the other. So wire 1, with the flow of current, exerts a particular force on wire 2, and wire 2 exerts that same amount of force on wire 1. So when they talk about this, and these are some equations that pertain to that. Okay, so I just wanted to get that out there, like after the break that we had, to look at this. I'd like to say one more thing here, and then we'll proceed further after I say this one more thing. They talk about magnetic flux, and it's pretty straightforward. It's pretty basic stuff, and like I said, when we talk about trying to determine what's happening with magnetic flux, it's a useful mathematical reality. It's a useful mathematical concept, and it helps us determine induced EMF and things of that nature. Number 6 would have been here. I just erased 5, guys. So number 6 here. We can talk about magnetic flux, and that's phi sub B. Electrical flux, electric field, the electric flux rather, would be phi sub E, but phi sub B would be magnetic flux. So you got this, and so we look at it. It'll stay consistent, guys. Put it in green. It doesn't really matter, but we got. Okay, so magnetic flux. Pretty basic stuff. I mean, in the vector analysis / sort of calculus realm, but more of just vector analysis at this point, you can say B vector dot A vector equals BA cosine theta. We said the electric flux, and we were able, and we said the induced EMF, N is the number of turns in a coil that's experiencing a change in magnetic flux. And we got this. This, if we're talking about a coil that's moving through a constant B field, way down there to your far left, the F vector equals Q V vector cross B vector, F equals QV cross B, wow, it really can explain this. If you're patient with it, do some of the mathematics with it, we can look at F equals QV cross B and actually manipulate it and actually be finding an EMF. This is a delta V. This is a change in potential, and we can find that, believe it or not, using a lot of the earlier mathematics and concepts, including, like I said, I cannot emphasize how useful this empirical relation as well, F equals QV cross B, and this empirical relation as well, that's very good, that helps us out. So utilizing this and playing a lot of different mathematical games, so to speak, you can talk about, regarding change in flux, you can talk about basically how a generator behaves and how the change in flux to which they arrive all occurs. So we got this. Run out a little bit of room, you guys, I guess, when I do this. So I think the red looked better, you guys, to be honest with you. At first glance, I guess. So we got this for magnetic flux. So again, we're going to get together again. Without a great deal of time between what I'm doing here, guys. I'm pasting a few of these together to kind of help you guys out and get us through this. After this, when we've finished all this, we're going to go into inductance. So we'll get to that very shortly. Take care.